Yeah, switched it on.
Okay.
Yeah, so
Okay, good afternoon, everyone. Good afternoon. Good afternoon. A couple of quick reminders. There is a homework due tonight. I will be posting another one tonight. Okay, that will be due next week. And you're going to have your exam the week after that. Right? Okay. And as I did in the during the last exam, the format will be the same as the last exam. You'll have a couple of days, 2-hour window, all these things. I will also have an exam review session sometime next week. This will be conducted via Zoom, and I'll let you know what the times are. Yes? I am mulling on it. I think I've been told by a lot of you that you have a final exam right after the System Dynamics final exam. And I think I will try to follow that format, though I cannot give you a 2-day window. It has to be a single-day window. Okay? All right. All right, but this is not finalized yet for the final exam. Yeah, we will send out an email, and some of you will read it. Yeah? Okay. So transfer function. Transfer function we defined as the following. Okay, so TF or TS is the Laplace of the system response divided by the Laplace of the input function. The system response is a dependent variable of the problem that you are interested in. If you have an equation of motion that tells you what the system response variable is going to be, x of t, for example, y of t, z of t, some function of time, input is some function of time. This is all performed in the Laplace domain. Okay, so all in the Laplace domain. Please notice something that irks me, and I beg your forgiveness for that, but it still really irks me. This is the spelling for Laplace. It is not L-A and capital place. Okay, please respect the person. All right, thank you. So this is the definition of the system transfer function. This is in the Laplace domain. We switch off the initial conditions when you do it. Set to 0 when you calculate the transfer function of a system. A system could have multiple transfer functions if it has multiple inputs. Okay, we saw this in the last class. And what I want to do today, which we started last time, we did not complete it, but I want to start afresh, the standard form of a transfer function. Of a transfer function. And for this purpose, we are going to consider the following nth order ODE. Okay, so nth order ODE subjected to an mth order input. I/P is input, and for proper systems, this is the definition of a proper system. I won't go further than that because you're going to come across this when you do controller design in the next sequence that you're going to take of this course. So usually M is less than, or in the worst case equal to, the order of the ODE, okay, of the system ODE. All right, and we wrote this down. Some of this could be repetition from last time. So this is AN dN x dtn n minus 1 a2 d square x by dt square, and then the remaining two, a1 dx by dt this is equal to the following: Bm BMF, so this is the mth order input function, okay, then the m minus 1th coefficient of that, then the second, first and the last coefficients, B2 So far, in most of the problems that we have solved throughout the semester, if you look at the forcing function, all of these terms are 0 except for perhaps the last term. Okay, that's what we have seen so far. In your recitation, where they solved the problem of base excitation, you would have seen that you would also have this particular term come into play. You will be revisiting that problem for the next homework. Okay? But this is in general. And then we say, okay, take Laplace transform on both sides, switch off the initial conditions. So the Laplace transform of the nth derivative is s to the power n. Laplace transform of the n minus 1th derivative is s to the power n minus 1, and so on and so forth. And so I have an s to the power n, n minus 1, a2s square, a1s, a0. X of s is the Laplace of the dependent variable. So in this case, the dependent variable is x of t. I'll note that down somewhere here. Input f of t and derivatives. And the output or the response is x of t. So we expect the transfer function to be the ratio of x of s to f of s. Okay, f of s is the primary input function and it has a host of its derivatives in there. Alright? This is equal to Laplace transform on the right hand side, same idea, Bm, the Laplace transform of the mth derivative of f is s to the power m times capital F of s. So this is Bm s to the power m minus 1, s to the power m minus 1, and all the way until the end. V2 s square V1 s V naught f of s. All right. And so the system transfer function can quite simply be written as the ratio of x of s to f of s. If I do that, I get t of s is x of s by f of s. Take the f of s term, bring it to the left hand side in the denominator, then take the terms that contain x of s, the s to the power n, s to the power n minus 1, bring it to the denominator of the right hand side. If you rearrange the furniture, you get the Laplace transform of the output to the input. Okay, so I write this out here. An all of this divided by the denominator. I'm sorry, this has to be the denominator and the numerator. Apple. So this is Bm s to the power m minus 1 and then the denominator, which is essentially the characteristic polynomial. So this is An Any questions so far? This is typically not the form we like to write things because we always want the coefficient of the highest order of s to be 1. Okay, so in the numerator as well as in the denominator, we take this fellow out, we take that fellow out, divide everything through. Okay, so one more step. P of s is Bm, which is the coefficient accompanying the highest order of s in that first polynomial, the numerator polynomial, divided by An, and we have the following. The numerator now becomes the following. It's s to the power m plus Bm minus 1 divided by Bm, because I'm taking that as a common factor, s to the power m minus 1, B1 by Bm, and B naught by Bm. All of this divided by the same story in the denominator. Okay, so this is s to the power n all right. This is what is considered the standard form of the transfer function of a system, but this can be further reduced because I see that there is a polynomial in the numerator, a polynomial in the denominator. I can find the roots of the polynomials. And typically you can, if you have a quadratic, you know how to find the roots. If you have a cubic, MATLAB knows how to find the roots. If I have an nth order system, I can always find the roots of the polynomial. They could be real and distinct, they could be real and repeated, or they could be complex conjugates. We have seen the whole plethora of these in our calculations, right? So if I write this out as the following, so this is called the standard form, okay? So this is some capital K, where capital K in this case is the Bm by An, and then if I have an mth order polynomial, I have m roots. If I have an nth order polynomial, I have n roots. So m roots in the numerator, n roots in the denominator. The factor k is essentially this creature here. And this is called as the gain of the system. Okay? So k is called the system gain. The roots of the numerator are called the zeros of the system. Okay? So the z1, z2, zm are the system zeros. What do you call the P1 and the P2s and so on? Anybody? Yes? The system poles. Thank you. We have come across system poles. They inform the stability of the system. What's the use of the zeros? It is not my business, because you're going to see the utility of the zeros when you take ME3360, which is system integration and controls. But let me tell you this, the system zeros are useful in controller design, that is design of control systems, and they typically will employ the method called as root locus plots. So the system zeros, the utility will come into play then. My business here in 3260 is just to provide you with the representative form of the transfer function. Okay? I'm not going to dwell more on that. So this is to be used in controller design. And for those who are curious, it's called the root locus plot. And in our limited capacity of system control design, we will come across the utility of the zeros when we study the Bode plots. Okay? So the system zeros we will study them briefly when we look at Bode plots. Hendrik Bode is the person who came up with Bode plots. He was from Ohio State. So, good stuff. Okay. Very, very beautiful way of representing system response in a frequency domain. We're going to do this next week. All right. So this is a standard representation. Why do we call the Z1, Z2s as zeros? Is because if S is equal to Z1, the transfer function becomes 0. It's as simple and elegant as that. Once again, I'm not going to write this out. Why do we call them as system zeros? In my lecture notes, I've spelled it out clearly. Please read my lecture notes. Spend some time looking at it at least. The system zeros are called that way because if I substitute S is equal to Z1, for example, the transfer function becomes equal to 0. Okay? That's why it's called a system zero. The poles, as I already told you, the system is built upon the poles. If the poles crack, the system is unstable. If the poles are on the right half plane, system is unstable. If the poles are on the left half plane, system is stable. All right? So we're going to solve some problems, examples, as we always like them. I'm going to pull this panel down. Are there any questions, please, so far? I have a question. I have many questions, but here is one. What happens when S is equal to P1? Yes? The transfer function becomes infinite. Absolutely right. Absolutely right. And that's the basis for what is called as H infinity control. Okay? So when the system S becomes equal to the pole values, the transfer function is infinite. When the system is equal to these zeros, when S is equal to Z1 or Z2 or Zn or Zi, whatever it is, the system transfer function becomes a zero. Okay? So perhaps I should write this down here somewhere. I'll write this down here. So when in the limit of S tending to one of the zeros of the system transfer function becomes equal to 0. So this is a very nice generic succinct way of capturing it. And then in the limit of S tending to one of the pole values, the system transfer function becomes infinite. All right, so what is our plan? Our plan is the following. We are not going to be worried about the utility of the zeros. We already know the utility of the poles. I will be given a differential equation. The purpose is take the differential equation, write it in the standard form, figure out what the zeros of the system are, figure out what the poles of the system are, and then draw the pole zero plot. You've seen the pole plot on the S-plane, right? You've done it for your homework or hopefully planning to do it. You will be doing the zero and the pole plot as well, okay? Today. All right. So first of all, I'm going to rewrite the standard form because we're going to compare our systems with that. I'm going to get rid of this. And keep in mind, why are we doing these things? There is a larger explanation in my notes, but quite simply put, the system transfer functions will help us understand system response in the frequency domain. Okay, the frequency domain is where we are headed next. So the standard form of the transfer function is T of S is capital K. Just a repetition. S minus P1, P2. Why is it S minus Z1 and not S plus Z1? Shouldn't that be a question that arises? It's S minus Z1 because when S is equal to Z1, the transfer function becomes 0. And that's the definition of a 0. That's why we want to write it in this particular form. Okay? But that does not necessarily mean that Z1 is positive or negative. It does not fix its value. That depends on the system. That depends on the governing system equation itself. So example, let's see. Here is an ODE. Three x double dot, 9x dot plus 6x is equal to 5 f double dot 40 f dot 75 f. Okay, obtain the system transfer function. So what is T of S? Obtain the poles and the zeros. What is the system gain? And then plot the pole zero plot, which will be used when you take control systems in the root locus figures. Okay, the root locus diagrams. Okay. Here is what we do. Take Laplace transform on both sides, switch off the initial conditions. Okay, so solution. Take Laplace transform on both sides. No initial conditions. So the Laplace transform of x double dot becomes s square times x of s. S times x of s. X of s. Common factor out. Okay? So this becomes 3s square 9s plus 6 x of s. Laplace transform on the right hand side. 5 times Laplace transform of f double dot is s square times f of s, right? So this is 5 s square f of s. 40 times s times capital F of s plus 75 f of s, or f of s is a common factor. Okay? Yes, good.
So I'm just kind of confused as to when we should like into a certain form so we can finally see the and stuff like that with the second order.
Not yet.
Not here.
We are not doing it here. No, we are not doing it here. So if you have to find zeta and omega n, then what you have to do is this coefficient should be divided through. Okay? We will be doing it very soon. Not yet. And I'm not sure why zeta or omega n should be coming here, because we are interested only in the system transfer function, you see. Okay, but if you want the zeta and omega n, you will have to divide through by 3. Does that make sense? Okay. A longer conversation, we can talk about it later too. All right. So if I now take f of s as a common factor, here is what I have. 3s square 9s plus 6 is 5s square 40s this is a 75 and a 5 there. Transfer function is x of s divided by f of s. Okay, so t of s if you want an intermediate step before I do this particular step, just to be on the same page with everybody, here is what you can do. Take the x of s, keep it where it is. Take the f of s from that side, bring it to the left hand side so it becomes a term in the denominator. Keep the numerator of the right hand side where it belongs, on the right hand side. Bring the polynomial, which is the characteristic equation of the system, onto the right hand side. It becomes a part of the denominator. And so this is 3s square 9s plus 6. This is the system transfer function. But it's not in the standard form. It's not in this particular form. So what should you do? You should take the 5 out. You should take 3 out, which is typically what you do when you want to get zeta and omega n. You take the factor out of the 3 and then write it in the standard form and do the comparisons, right? So you still do the same thing here, except that you are not looking for zeta and omega n. You see, I still have to do that. Okay? So that becomes 5 by 3. If I take 5 as a common factor, it's s square, 8s and 15. People in the back, can you see my writing? S square 3s plus 2. We're getting there, getting closer to the standard form. It's still not in the standard form, as you can see. Which means I need to find the roots of the numerator. I need to find the roots of the denominator. Okay, which is quite simple in this particular situation. So T of s is 5 by 3, so that becomes the system gain, which is capital K, if I do the direct comparison. Roots of the numerator, s square, 8s and 15 is s plus 3 times s plus 5. It's fairly straightforward, so please figure it out. The denominator polynomial can be factored into s plus 1 times s plus 2. Okay? This is now in the standard form. So every time somebody gives you an equation of motion, you're going to do this multiple times when you do control system design. You always have to bring it to the standard form, the system gain, the meaning of which will become clearer later. I'm not interested in interpreting it for you today. The system zeros, the system poles. We know the system poles. They talk about stability. So by direct comparison between the standard form and this creature here, Z1 is minus 3, Z2 is minus 5. So compare with the standard form. First of all, m is equal to 2 and n is equal to 2 as well. Right, I have a second order polynomial in the denominator, a second order polynomial in the numerator. Then the system zeros is minus 3, minus 5. The system poles, minus 1 and minus 2, real and distinct, negative real part. The system gain, capital K, is 5 by 3. I want to see if there are any questions on what we have done so far. What are the steps? Take the ODE, write it in. If you want, you can start off by writing it in the standard form, no harm. Okay, you can divide through by the factor of 3, write it in the standard form. You will have a factor of 5 by 3 taken as a common factor out on the right hand side. Take the Laplace transform on both sides, switch off the initial conditions. The transfer function definition is the input Laplace transform on the denominator, the response Laplace transform in the numerator. Compare it to the standard form. Here are your zeros and poles. Okay? Now, we have what is called as the pole zero plot. It's plotted on the S plane. Same thing as what we did for the homework. On the S plane. Real part of S, imaginary part of S. I will be plotting the poles, I will be plotting the zeros as well. So this is the convention that we follow. Look at Z1, look at Z2. Okay? Those are essentially the roots of the numerator. Okay? So look at the right. S is equal to Z1 is minus 3. So the real part of S is minus 3. Imaginary part is 0. Does this make sense to everybody? I'm looking at the first 0 of the system. It has only a real part, it has no imaginary part. Likewise, these are the zeros. S is equal to Z2 is minus 5. System poles, the denominator roots. S is equal to P1 is minus 1. So the real part, no imaginary part. Same story, okay? S is equal to P2 minus 2. The real part is minus 2, imaginary part is 0. You plot the poles, typically with a cross mark or a filled circle. We've been using a filled circle with a cross mark. You can use either, but your book follows the cross mark. Okay, so on the S-plane, I'll follow your book. There are a million books on control systems, each one with their own idea of what is right and what is wrong. So the system poles are marked with a cross. Okay? The system zeros are marked as unfilled circles. So I first mark the poles, -1 and -2. Then I mark the zeros of the system, which is -3 and -5. There are no imaginary parts for any of them, so it is possible some of them could lie on each of the quadrants rather than the axes themselves. Okay? There's one here, -3, I'm sorry. -3, -5. So these are the zeros. Makes sense, the filled circle looks like a zero. These are the poles. And these types of systems, where you see that there are these zeros present, such systems have what is called as numerator dynamics. That is, there are some funky things happening in the numerator of the transfer function. You change the numerator, you change the coefficients. Perhaps if you're studying a step response, this could have a magnitude of the peak, could reduce, the peak time could be shifted, so on and so forth. Okay? Is the system stable or unstable? All the roots are on all the poles, I'm sorry, from now on there are multiple roots. All the poles are on the left half of the S-plane, so the system is stable. And please note, stability is described only by the poles. It's not described by the zeros. The zeros have nothing to do with the stability of the system. And when you do controller design, there could be some very interesting things that could happen. Okay? For example, you could have the pole and the zero being the same, which means that one of the poles and one of the zeros in a system could cancel each other out, and that's called as a pole-zero cancellation. It has ramifications on the behavior of the system. Don't worry about it. We are not interested in it right now, but you will come across it later. Okay. So this is one example. I have another example. I want to see if there are any questions so far. Given ODE, write it in the standard form for the transfer function. Figure out the zeros, figure out the poles. This is the pole-zero plot. Okay. It's on the S-plane, real part, imaginary part. Poles are marked with a cross, zeros are marked with a zero. Second example. You're told that the system, a dynamic system, has the following zeros and poles. The system has the following zeros. Z1 is -1, Z2 is -3. It has the following poles, which is -2 and -4. The system gain is given to be equal to 3. What do we need to do? It's the inverse problem, right? If you are given the transfer function, find the poles, zeros in the gain. Now, given the poles, zeros in the gain, find the transfer function. Find the system model. What's the dynamic model of a system? Is the ODE of the system. Just looks like a scary word. Okay? All right. You start off with the standard form of the transfer function. The standard form, capital A, S minus Z1, Z2, M roots on the numerator, N roots on the denominator. So this is S minus P1, P2, what's the value of M in this case? Has to be 2. What's the value of N? Has to be 2 as well, because there are the only things that are given to us. So just by comparing, so M is equal to 2, N is equal to 2, and all I have to do is substitute for Z1, substitute for Z2, P1 and P2, substitute the gain. It's as simple and silly as that. Right? Here is a task. Complete it, eat the banana, move on. So that is 3 S minus Z1. S minus Z1 meaning Z1 is minus 1, so minus of a minus is a plus. So this is S plus 1. And likewise, S plus 3 divided by S plus 2 times S plus 4. That's it. Okay? But I want to write the system model, the dynamic model, right? Which means that I have to do a little more set of manipulations. So this is fine. Great stuff. To write the system model, I say the following. So say, response is some Z of S. Now who cares? Could be some alphabet. Let's say the input is G of S. That's your choice. You can call it F of S and X of S if you want. I'm tired of X and F, so I'm putting G and Z. So what's the transfer function? It is a response by the input in the Laplace domain. And for this particular system, it's 3 times S plus 1 times S plus 3 by S plus 2 and S plus 4. Do you all see where we are going with this? What should be my next step? Yes?
I'd expand the top and bottom.
Expand the top and the bottom, and then? Yes?
Kind of like cross multiplication.
Cross multiplication, and then?
Inverse Laplace.
Inverse Laplace, and then we go. Alright? Great stuff. That's exactly what I'm going to do. Multiply the top and the bottom. So this is 3, S plus 1, S plus 3. Okay, so I directly do it as 3s square. I get 4s, so 4 times 3 is 12. And then 3 times 3 is 9. Divided by s square, 6s plus 8. Now the problem is, we don't know if this gain is coming only from the numerator or is it also coming from the denominator. Right? Because usually we have seen it written as a fraction. But we can't do anything about it because nobody is telling us what it is. I can only work with what I'm given, right? So unfortunately, I will have to assume that the 3 goes here, and then whatever is in the bottom is 1. It goes with the other character. I take cross multiplication of these two. S square, 6s plus 8. Z of s is 3s square, 12s plus 9. G of s. I'm going to squeeze in the answer right here. Okay. Invert. Wherever I see an s square, I get an x double dot or a z double dot or a g double dot. Wherever I see an s, I get a z dot or a g dot. Wherever I see nothing, I get x of t or z of t or f of t or g of t, whatever is attached to it. So I have the following. This is now going to be z double dot plus 6z dot plus 8z. This is equal to 3 g double dot plus 12g dot plus 9g. This is the system model. Any questions so far, please? Yes, yes.
So that was the inverse Laplace that you took to find that?
Say that again, please.
That was the inverse Laplace?
Yes, yes, the inverse Laplace. So if I have s square times z of s, right, then the inverse Laplace of s square times z of s is z double dot. Okay, and so on and so forth, right? And we don't have any initial conditions, so when you take the inverse Laplace of this term, I don't have any z of 0 or z dot of 0. Okay? Okay. Any other questions, please? These are surefire questions in your exam. They're not very terribly hard if you practice them enough number of times. Okay? This is just easy meat. Okay. We move on to another useful and very interesting part of this section, and they're called as block diagrams. Look at the progression of thought. We started the semester with an introduction to system dynamics, which essentially told you what the end goal of this course would be. Given an actual physical system, use simple tools to model it, obtain the mathematical model, solve it using Laplace transforms, understand the system behavior. That was the overarching theme of this course. Then we slowly got ourselves understanding, okay, what are the characteristics of an ordinary differential equation? What's the order, what's the degree, time invariant, homogeneous, linear or non-linear, and then we started looking at mechanical systems. Try to obtain the equations of motion, got used to the rudimentary aspects of springs and dampers and so on. Torsional systems came next. And then we said, okay, we have seen enough of one particular type of system, let's now study the qualitative and the quantitative behavior of generic systems. First order response, second order response. Second order response, we studied free response, we studied step response. You have time delayed responses, which you're solving in your homework, and I have an example problem up. And now, we are slowly saying, okay, I'm going to move to electrical systems, which are better analyzed in a different domain, which is the frequency domain. And so for that, I need to define these new terms, called as the transfer function. And the block diagram is just taking the transfer function and making it more easier to visualize it. So block diagrams are tools that provide a visual representation of the dynamic model. Okay? So this is a visual. representation of the system dynamic model. If I'm given the block diagram, I can obtain the system model. Okay, given the block diagram. We can obtain the system transfer function. If you know the system transfer function, you know the stability of the system, you know the zeros of the system. You can perform controller design later on, next year, next semester. You can also obtain the system dynamic model. You can obtain the transfer function and obtain the dynamic model of the system, which is the system ODE, x double dot plus 3x dot plus 4x is equal to f of t, right? Something like that. Keep the big ideas in mind, the details will come later. And the biggest idea of this course, and I don't mind spending time talking about it, is the following, which I just explained. Take a real physical system, simplify it, model it using some basic tools, springs, dampers, wires, capacitors, resistors, and so on. Obtain the mathematical model. It will be an ODE because it's a linear system. Use Laplace transforms, solve it, move on. That is all we are doing in this course. Everything else is just bloody details. Okay? So when you do block diagrams, there are certain fundamental aspects of the block diagram that are necessary to understand. So fundamental parts of block diagrams. Signals. What's a signal? Yes. Input or output? You're right, but can you characterize it better? What does a traffic signal tell you? It tells you something, right? It conveys information saying, hey, red means stop for some people, green means go for all people. The same thing you do in signals as well. Signals are functions of time that carry some inherent information about that phenomenon. Voltage signal, a force signal. A force signal tells you, okay, what is the amplitude of the force? How does this force oscillate over time? Okay, so signals, they are information carriers. Block diagrams are done in the Laplace domain. I want to write that statement here. And so for us, as you rightly pointed out, we have input signals, we have output signals. So we call them as x of s, f of s, and so on and so forth. These are typically represented by arrows. I could have an arrow, and on top of that arrow could be some g of s. So what does this arrow tell you? The arrow tells you, hey, here is a signal g of s. It is propagating from the left to the right. As simple as that. Okay? That's one of the fundamental parts of a block diagram. The second one is a summer. As the name implies, it adds or subtracts signals. So I would have it represented by a circle.